All right, happy Tuesday afternoon. We're starting the second half of the term. We've done 4 lessons. We promised 8. The last lesson's a little bit longer. We're going into things that are a little bit larger in scale necessarily, but we're going into things that are likely to make serious impacts. One of them will be sea level. You've heard a lot about rising sea levels and all of that business. We're going back to the geologic time on time scales of about whole glacial cycles, which is the 100,000 year time scale. We're going to talk about large sea level changes, real serious stuff. And actually sort of one of the more dramatic things you can do to the face of the globe on these time scales. So I'm going to get ready with that. Before I get going, anything anybody wants to talk about, raise a question, debate, pay money, anything, nothing like that? Okay, first of all, since we're halfway through the term, I promised to update the grade distribution. There's 1 or 2 of them here that are a glitch, but basically that's a pretty nice grade distribution. One of the things that you find, or I find, you probably noticed that you can get very hard to get a perfect score in any one exercise, but it's really easy to get 8 out of 10 or 9 out of 10 or something like that. And if you do that, and you consistently do that, you're going to be clustering right in this group here, which is in fine shape as far as I can see. Again, the challenge with folks that are down in these categories is they miss an assignment. The challenge with this person up here is they keep doing all the bonus points. I think I articulated that's the way to get a good grade in this class, is just do everything. It might not be, you know, I'm not dealing you exactly in technical content being, right? I'm dealing with you how you're handling the information. Questions on that? So you can scale yourself and see where you're getting. We'll eventually have 800 points. If you go back to the syllabus, it'll tell you where your letter grade will fall. All right, let's get into a quick ecological reorganization. I was pleased that several of you talked about the Younger Dryas and or the second question and used my little mantra. There's only 3 things that you can do as a mechanism if the environment changes, and one of them is for adaptation, and one of them is to move, one of them is to evolve, and one of them is to die off. The evolution one is usually not talked about too much in this class because it takes very long time scales for you to change. I mean, Homo sapiens has only been around a few 100,000 years, which is nothing in geologic time, but it took that long to evolve it. Well, this was a study that I saw yesterday, basically, of some fish in African lakes. It's a particular type of fish. And the point is that it's a recent example of evolution. And of this type of fish, there's sort of figuratively a couple thousand different species. And they live in these one of them is around Lake Victoria, which is in central Alaska in the Big Rift Zone. And Lake Victoria is sort of 40 meters deep, but guess what? Not at the same time Lake Huron was, but at an earlier time during the Ice Age, it was dry. Another 40 meters of water disappearing and coming back. So folks have a time slice that there couldn't be really a lot of fish going around in here then because it was dry. But these folks played around a little bit, and one of the things so they have a starting point for timing of evolution. Well, if you read in the fine print, they say the rapid and extensive radiations, that means the increase in the number of species of this type of fish, including 500 of them, tropic levels as kinds of lakes in 16,000 years. This would be unheard of as a concept just a few years ago. So the DNA studies are telling us that things can evolve on tens of thousands of years, which, you know, I find quite remarkable. It's not long enough to get you through the Younger Dryas. It's only 1,000 years long. But it is time to do that. So that would be an answer to the last question. So this is that point. They show this as a diagram of a couple species. These are a couple 100,000 years old, and they go along. And then all of a sudden, there's this dry spell, and it's blown up here, where lo and behold, from this branch, it just branches out into 500 new species or something like that in the 16,000 years. Pretty impressive. Point is that a lot of concepts I might have taught a few years ago keep changing on me. Okay, back to something I'm a little more familiar with, and it's not as slow as a glacier because glaciers are not as slow as you think, but the glacial cycle. And this is the 100,000 year pulse beat of the last few million years on the planet. And the 100,000 year cycle has a certain characteristic shape to it. So we're talking about hundreds of thousands of years, 400 to be exact, and it's a sawtooth pattern. You start here, which is basically today's conditions. We're in the warmth part of it, and it takes a while to oscillate down and gets warm rapidly. Takes a while to oscillate down, get warm rapidly. Takes a while to oscillate down, get warm rapidly. Takes a while to get warm, guess what? Gets warm rapidly. These terminations, the red arrows, the end of the ice age, are a topic that's been driving us nuts. It looks now like this is so rapid that they can't measure it in some time scales that we typically use. It's a couple hundred years-ish. It's only a minimum of a couple hundred years because that's as tight as we can measure the thing that we're tracking, or that those folks are tracking. So these terminations are another whole problem. But the pattern we're concerned about today has to do with during these glacial times, you build these ice sheets. And you take a lot of water out of the ocean. And then it warms up, so the water melts and goes back into the ocean. So we're going to look at the return, not these necessarily, but the return of the return into the oceans from the ice sheets over a few thousand years. Sort of takes 6,000 or 8,000 years to get complete, but the first part of it's pretty fast. So the ice age is characterized by cold times around the globe. All glacier systems that we know have expanded at that point. Not so much expansion in Antarctica for local meteorological records, but you have coverage of the North America, and I've alluded to it 2 or 3 times. It ended in Sharonville. And also Northern Europe and parts of Eurasia. All of these little ice masses also expanded in through Alaska and whatnot, but the big players in the deal are this person, or this ice sheet, and this ice sheet. This is small compared to this. This is something like West Antarctica today, and that's fine. But we had lower sea level, plants are redistributed. Of course, they physically couldn't live on the glacier. We're talking something on the order of 5 to 7 degrees, depending on where you are, temperature change. So we started with the 8.2, which was small, ½ degree, went to the Younger Dryas, which is a couple degrees. Now we're up in the 5 degrees Celsius as an analog. And this rapid warming is the characterization of these terminations. Okay, so that's the ice age, and sort of to set the stage. We're not going to go too much beyond that. The ice volume mirrors that pattern, though. To build those ice sheets, you have to do something. Now, this is time scale going the other way, just to keep us on our toes. And this pattern broadly follows what we've been looking at before. If we talk about today's sea level as a reference point, then by tracking these particular critters in the ocean, you get a little bit smoother pattern, but you get the same thing. It's warm here, and it comes down, and then it shoots up. And we're going to look at that, of course. There's a lot of debate about this. Why? That's a time when sea level might have been several meters higher than it is today. A lot of debate, contention on that. I haven't seen a drop down, knock down, drag out, convincing argument one way or the other yet. Quite a bit of hints, though, that there's higher. And people would like to study something that was higher, because that's an analog for what might happen in the future. All right, so that's a pattern of sea level, the relative sea level. We're going to get into how you excuse me. I'm going to give an example of some things that happened that may support this concept of a higher ice sheet, higher sea level. And then we're going to talk about the mechanisms, and then we'll go from there. So mangrove forests, they grow at sea level. They have their roots in the ground. They're sort of at that water level. So here's a study from, where did it come from? It's in Latin America someplace. But here's a 10,000, or that's a 100,000-year-old forest. That's a mangrove forest, but it's 9 meters above sea level. So why did you get a mangrove forest that may be a few 100,000 years or 100,000 years old that was above sea level? Well, that could be that little nip. So we get hints like this, and that's interesting, and that's the higher end of the sea level. Most of what we're going to talk about today is how did it get the present day level? What's the pattern of the present day level? It's all about water. It's all about the redistribution of water. Your homework exercise is a lot about quantifying the distribution of water. So you have land, mountains, you have sort of land, you have the oceans, and you have the bigger ice masses here. They've stuck little glaciers up in here. We talk about the hydrological cycle as moving water from the oceans into the atmosphere, precipitating it out as rain, and we talked about that for the intertropical convergence zone. The water that gets there, though, generally runs off on rivers, the Amazon, the Ohio, yada, yada, yada. Part of it actually goes into the ground. Now we're sucking it out of the ground at sort of unprecedented rates, but you can see that if everything's in balance, there's exchange up here. There's a lot of water flowing out of here, but it really doesn't change sea level. This rains, comes down here and gets evaporated and goes up again. So the sea level stays the same. This amount of water is so much that it's figuratively the rainstorms, the thunderstorms, the Ohio River is figuratively a drop in the bucket. You could shut the Ohio River off and sea level wouldn't care. You could dam up all that water that comes through eastern half of north of the United States and you couldn't tell. I think that's true. All right, so then there's a second concept here about is the sea level level. Well, water seeks its own level. We always get that. And that level actually is gravitational potential, which is not exactly the same. So what we're going to see is a graph in a few minutes where it doesn't look like sea level's level because it's not. So the gravitational thing has some humps and bumps to the surface of the ocean. All right. So far, so good. If I plot in round numbers the sea level since the last glaciation, way over here, here's glaciers. Glaciers were in Cincinnati about this time here. That was as big as the ice sheets ever got. That was as low as sea level ever was. As we came through time to the present, there's a slow rise and then a rapider rise and then it tapers off. In broad terms, that's the sea level rise. The thing that's really impressive about this is not the shape of that curve, it's the amount of water. Someplace in the number that we generally use now is like 127 meters. 127 meters of sea level. If you put sort of 10 or 15 meters on Florida, you're going to kill it off. All right, so I want to impress upon you that that's a big deal. And then second of all, we'll think a little bit about other ramifications. There are some challenges to the exact pattern of this. And I don't think for our purposes we want to get too far into that because it's a quagmire. There's theoretically sometimes when it's really fast rate. I think the fact that we're going to deal with this kind of change over 8,000 years or something is significant enough for our purposes. And what's happening now? Well, it's really been stable. This is a best metric of the whole sea level of the planet. And it's basically been that way for say 6,000 to 7,000 years. Slight rise. When you read about the newspapers, when you read in the newspapers of the sea level changes that people are talking about, measurements, and you can find this, they're talking about these kinds of sea level changes. Not tens of meters, tens of millimeters, or a millimeter, or something like that. So it's going up. You wouldn't be able to plot that on this map. Okay. Rates. Does it matter? Rates. We've had rates, we've talked about rates before. So if sea level comes up at this rate, and then at this rate, and then at this rate, does it matter? Yeah. I mean, if you try to build a house here, you're going to get swamped out in a mere 1,000 years. In 1,000, that's 2,000 years, so that's 1,000 years, 20 meters. You're going to have to move all the way across Florida. If you worry about now, the rate isn't really much. You just have to worry about moving off the beach, so to speak. Okay, so I want to just show the geographical imprint of this. If we look at the world today, from the North Pole, Greenland's the last big ice sheet. We've talked about if you get rid of all that, you're going to get 7 meters more of sea level rise. It's possible to kill off Greenland, but it'll take 500 or 600 years. Everybody's not convinced that you can do it, and you're going to maybe do parts of it, but it doesn't matter. It's a potential source of water today. Back in the day of the Ice Age, here we are in Cincinnati, ice sheet joining Greenland, and then this ice sheet roughly in these numbers. Okay, so let's look at these shaded relief patterns. This shows topography. Red is high, green is low, blues are deep, and the color band is about where the present day shoreline is. So let's pick on the gentleman in the red hat. We're not going to pick on you. We're going to get you going with a discussion here. If sea level is going to change, what areas might be impacted based on just this geography of the present day oceans?
Well, what I think is that it would impact everywhere.
Okay.
Because of the way water is. So sea level will rise as one, like a whole.
Rise as a whole. Okay. I don't remember if I have a slide by this, but let's follow this game. So there are kinds of coasts, right? I come from Maine, the rock-bound coast of Maine, or whatever. There's steep cliffs there on the coast. So if sea level goes up half a meter, it goes up half a meter. If you live in Florida, the land looks more like this, right? If you go up half a meter, where does it intersect the land?
It's going to intersect it like above where it was before.
A meter higher. But because it's on a slope, it's the same thing with the sun's rays. It's going to be a lot further away, depending on how I'm drawing the slope either way. What I'm getting at here is that we look at areas that are shallow, the light blues, as areas that might be more receptive. Okay, and the Bering Strait is one of those areas. The Bering Strait, during the Ice Age, you could walk across this, and people did. I mean, all the water, there was no water there. You couldn't get a boat from here to here. All right. See, that's all ocean now. That's all land then. All right, let's look at a few more geographical places. This is an equator view looking here. Here's our ice sheet over, here's us in Cincinnati. There's ice in Europe, and there's a little more ice in the Himalayas and all of that. Any of this geography strike you as being different because now we've got ice sheets there? Any place that you can think of or you'd look to? Some projections aren't going to be good. Is there anything that doesn't look like it, you normally think of it, the geography of the place? Around India. Here?
A little bit up.
This.
No, like where the snow is that area.
In here?
No, like where the white part is above India.
Yeah, well, this is India. You're right. I'm sorry, we might be.
Saying right above India.
Oh, this here?
Yeah.
All right, that's the Himalayas. That's high. Sea level is not impacting that. The white is the presence of more snow and ice there. but sea level doesn't go up that high. All right. Any place that you know of that higher, lower, or impacted during the Ice Age? Excuse me?
Near Australia?
Australia. That's not on any map of Australia you've seen, is it? So Australia has a disturbance down here to Tasmania, or not a disturbance, it has land. And there's a protuberance up into here. Okay? You want
Say Florida, it just doesn't look as like sharp as usually is.
Florida's not quite as sharp as it is. I've actually got a blow up of that. We'll get back to that in a minute. Okay, go ahead.
And like the islands in East Asia,
In where?
like the Philippines or
This?
right there.
Yeah, this is impressive. So we've got a little closer zoo of that. Recognize Europe? The Mediterranean didn't dry up necessarily during this time. The Black Sea and the Crimean Peninsula weren't connected to the Mediterranean. You couldn't take a boat through there regardless of the political ramifications. Britain and Europe were truly united, not just economically, but physically, geographically. The North Bay here, you didn't have any of the Baltic Ocean. On it goes. Another place is, the gentleman just pointed out, Indonesia. Today you have the peninsula here, you have Australia over here, you have Papua New Guinea in this part, but it was all one big landmass at that time. Okay, so these things are telling us that they're less than 120 meters below the present day ocean level. And I don't know why we said that one again. I think because we were going to go to Florida, as the gentleman pointed out, present outline of Florida. This doesn't take it down to the lowest level, but this was an article that showed up a couple days ago about an archaeologist who dives and is recovering artifacts from around the Florida coast. Now they aren't Ice Age artifacts. She hasn't gotten that far out, but they're sort of 8,000 years. So you see a lot of distribution in present day Florida. You see a lot of archaeological sites. You don't see them on this land that would have been land at 15,000 years, 13,000 years, 12,000, 10,000, blah, 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 because they haven't looked for it. They find occasional ones, but it's more by chance. This is a big area to cover. You've doubled the size of Florida. I don't know what that does to the electoral votes, but it's double the size geographically. Okay, so sea level matters. Some places not so much. This is back to the argument of what's the slope look like. Where it's shallow, a lot. Where it's steeper, not so much. Okay. Where did all this water come from? I'm going to delve a little bit into my favorite ice sheet, the Laurentide. In broad numbers, it started off as a big mass, and then it, not exactly crescentic rings, but it disappeared. So we have it down here, and then we have it going away for 6,000 or 8,000 years, closer to 8,000 years or whatever. Finally retreating back up into Canada. There's a big, well, I'd say 12,000 here. The big change between 8,000 and 9,000 years ago, we've been talking about that time slice. We've been talking about that. That's the breakup of these lakes and the flood of water out. And that, but it took a long time. You can't just sunshine, you put an ice cube out and let the sun shine on it. It doesn't melt overnight necessarily. Depends on what your eyes. If you have a big bag of ice, it takes longer to melt. This is the biggest bag of ice there is. It's the equivalent of those 127 meters of sea level. This is about 88, is that about right? Something like that, 80, 90 of them. It's not 100% of it, but it's quite a bit. So you can get a way to melt this. It does get warmer, it's going to melt around the edges and slowly go away. That's going to provide some sort of consistent, depending on how close these rings are, flood of water out into the ocean, down into the Gulf of Mexico, back into the Pacific Ocean. If we plotted just the sea level rise from the ice sheet, it would parallel this in large, not from up here, the ice sheet goes away. That's kind of why it stabilizes. But that's track of the ice sheet. You've got another ice sheet in Europe doing the same thing, but it's not as big. All right, enough of that. Now, it turns out there are two ways to get rid of an ice sheet besides just melt it. The first way is you melt it because it's a solid. It's a strange solid because it's a solid that's less dense than its liquid phase. And you simply add some energy to it. Again, it's a slow, methodical process. Effective. Takes a couple lifetimes to see the difference. There's a second mechanism called calving it. That's when you suddenly remove it by the fact that it's floating, and all of a sudden it breaks up and it catastrophically discharges icebergs. And so you've all seen probably video someplace of icebergs breaking off a glacier someplace, and that's the calving process. The first, because it floats, there's a lot of mechanisms in this, and it's so important that it gets its own lesson, and it's the next lesson. So we're not going to go much further into calving today, other than say it's a lot faster, that's why we're going to study it. So slow and fast. And this calving process is marine ice sheet instability hypothesis. All right, melt pools. Pretty picture of the Columbia Glacier. Water on the top. These are trim lines where the glacier's been thinning for about a century. All of this stuff is breaking behind where the helicopter was that we were taking this picture. There's the calving margin, and that's another whole story. I'll show you those calvings here. But this is thinning. This is what the ice sheet would have looked like. It's got water on the top. The water's helping speed it up a little bit. The water, this is the bottom of a smaller glacier in Iceland. Drip, 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 always producing water, producing the water. A lot of ice, produce a lot of water. We like to quantify how much melt can occur, and it's not simply temperature. It's how much the temperature is above a certain normal, above freezing, but also how long it is. I mean, it's one thing to have a hot day for one. You want to get rid of my favorite ice cube. You can do two things. You can shine a bright light on it for one day, or a bright heat lamp, or a dull heat lamp for several days. You do the same energy, takes a different length of time. So there's a term called positive degree days. It's very much like heating degree days, if you've ever run into that term, to keep your house at a comfortable level. It's the deviation from there, and the amount of energy that you have to do is a product of the time versus how much the deviation is. On a hot day, more than a cold, a day that's close to temperature, but a lot of energy if you have to do it for day after day after day after day. Anyway, we're talking about a millimeter. We're talking about that much a day-ish. Under conditions that they would experience. So it takes a while to get rid of 3,000 meters of ice. A concept, just to bring this in, because this is my favorite topic. So we talk about a glacier. We talk about it as a piece of plastic that slides down this slope, slides or deforms down this slope. We note that anything that's on a slope like this has a temperature distribution. And as I go up in the atmosphere, what happens to the temperature? The gentleman in the black shirt? No, I think it's you. Yeah, the air temperature goes down as I go up in the atmosphere. You know why? Gets further away from the Earth, but it's something to do with the atmospheric density too. It's less dense, right? So it gets colder as you go up. And so it turns out that you can have a glacier divided into two parts. Part one that's down low, that melts all the time-ish, or at least in the summertime, doesn't melt in the wintertime. But an upper part that doesn't melt ever because it's above the local freezing level. In my glacial class, the graduate class that I have after this, we calculated how far above Cincinnati you'd have to be to get a glacier, and it turns out it's a couple kilometers. So this is a conceptual idea to bring home this business of the melting. Again, it's slow and methodical. Any more questions on how to melt a glacier? Lady in the white shirt, third row. Do you want to melt a glacier? Do you want to keep the glacier or do you want to get rid of it? Pick your battle. Do you want to get rid of a glacier or do you want to keep it? Oh, wrong choice, but I'll let you go with that. So if you want to get rid of my glacier, now I'm not going to be happy about that. What's the best way to do it?
Well, if you want to get rid of it fast,
Calve it, throw it in a bucket of water.
Yeah.
Glacier's kind of hard to move, so the bucket of water had to be there before. The glacier I just showed you from Alaska, that's longer than Hamilton County is wide, so you can't just make a bucket here, but that's okay. And what else can we do? We can melt it. Now, how do you want to melt it? Are you really anxious to get rid of this glacier, or do you want it to linger in anguish for a while?
well, it would like linger because it's slower.
Excuse me?
It would like linger because it's like slower.
It's slower. Right, but if you could control, what would you have to control to decide how long before its fate was up?
The temperature.
Or this is the temperature. This is how long that temperature is applied. So if the glacier will stand there and take 80-degree heat, not very long. But it can handle a day or two. You'll get a lot of water. What you want to do is bring it up for a longer period of time. And that's what happens when climate changes. You get both the temperature increase and you get warmer temperatures above freezing. So that's how you get rid of glaciers, and all the glaciers on the planet are except for some in Antarctica are basically melting today, which is not a surprise. All right, glaciers, we like them in equilibrium, balance. If you know the area of the ice sheet and you know something about the temperature distribution, you can actually talk about the fact that with a given temperature it's this much. You could actually calculate how much water it is. Lady in the white third row. If I actually calculate how much water was, who cares about that? Why would I want to do that? If you'd assume that we can do the calculation, right? Why do I care about that? How much it would melt by. And what are we going to do with that melted water? We're going to run it down into the ocean. So instead of the natural hydrological cycle, which cycles it, this additional water is going to run into the ocean. And depending on how fast we torture the glacier, it's going to go up incrementally. So this is a calculation that one can do. Your homework exercise today is going to do this in round numbers. And we're going to find out how many cubic kilometers, actually tens of, would it take of my glacier? How big a glacier do I need to actually raise sea level a meter? I'm making it a meter because the math's a lot easier. But I mean, do I need, something the size of Hamilton County? Hamilton County, you wouldn't see it. Something the size of Alaska? Maybe, maybe not. So that's what we're going to do. So pay attention to the rest of this. A mass volume to be estimated. And will the sea level rise? It will, if long as the glacier was above sea level. If it's floating, which is another case, we don't worry about it. All right, let's get her out of here. There's a real complication to figuring out the former distribution of sea level change. We've talked about it as being one graph. It's not. Why? Here's a cross-section of the Earth. The two layers that are directly under the Earth are called the lithosphere and the mantle. These are something like 10 or 15 kilometers thick or something. And so it's the solid rock. But the solid rock's not so solid when you put something on it that's the size of North America. It bends. It depresses. And it bulges down. So you stick this thing on here, and the crust goes down here. This stuff is a little more viscous. This is not so viscous, but it can bend. And then that moves the mantle away from the center of the ice sheet. By the same token, get rid of the pesky glacier. There's a hole where it used to be, and the hole will decide to slowly rise back up. Why do I care about it? I don't have to change a glacier a bit, but I can let the lithosphere come back into balance and rise sea level right there, right? This is my sea level. I'm in a hole now. And just by here, the water's deep, and then it's rising back up, and I might get my feet wet standing in the center of the ice sheet. Hudson Bay today is the center of the ice sheet. In fact, is still going up today. It takes a few thousand years to do this little trick. So they do arrows, flow the soil, solid, this should be solid earth. And so this crustal deformation, let's just call it that, they've got fancier names, but it ends down and it'll pop back up. This is something happens on the continental scale, not locally. We can look at evidence here in southern Ohio because the glaciers got here. There's a couple river systems that got jacked around a little bit and tilted. I mean, we can see evidence of this. It's subtle here in Ohio. If you went up to the Great Lakes, you could see it more. So what I'm trying to get a point across, though, is that sea level depends on your reference frame. There's not an absolute number. The graph that we had with the 127 meters is for aesthetic purposes. But there's no place on the globe where it went up exactly 127 meters. Some of the places went up more, some went up less. We call this a relative sea level curve. We can go to any place and we can look over time, back 8,000 years, and we can look at how high something was that was at sea level at the time, 8,000 years ago, and now it'll be 30 meters above where it is today. 5,000 years, 20 meters ago, and on it goes. And these data points we use to reconstruct this relative sea level all the time. It's an interesting property of the crust. We can measure it exactly. That example happens to be from Antarctica. Those happen to be places, and most of those are marine mollusks, shells that would live at the sea level in the ocean. So sea level changes. So gentlemen in the red, why do I care about crustal deformation again?
Because even without the ice, the sea level will rise.
You had to have the ice to get it deformed.
But the ice, it's another factor that creates a level outside of the liquid.
So it's another factor to talking about sea level. It also is a miserable thing to account for if you're going to predict sea level rise. You have to know what this rebound's doing now and in the future. Because actually, if you take water and put it on the ice sheet, it'll also depress the crust. So the net result of all of this is, fancy a term for the same thing, an isostatic adjustment. This is the current situation. The sea level is changing just because of this, but it depends on where you're at. Gentleman in the orange shirt, way back. So here's the midpoint of the crustal movement, right? So everything in red is rising sea level, relative sea level. Everything in the blue is sinking sea level, right? What's an interesting area to you? What's a pretty, where are the pretty colors?
Like right around where the ice sheets were in North America.
Like right around here? Yes, here's us in Cincinnati. Look at that, we're right on the blue-yellow line. That's about right. It's actually a little further north than here, than Cincinnati, but that's okay. What other areas are interesting? Everybody see the little yellow lines and blue lines? Right there is the break.
Like right above Russia.
Above Russia, the blue here.
Yeah.
So what's happening there? Is it going up or going down?
It's going down.
It's going down. Relative sea level then, that's the crustal movement. So is the water coming up or is the water going away?
It's going away.
Millimeters a year. This is going away if we take this value. Okay. We might have the signs mixed, but I'm not worried too much about that. Gentleman beside him, he picked out all the pretty colors. What are the bulk of the oceans doing, though? Are they redsies or blue or green? Redsies or bluesies? So there's blue down here in the southern hemisphere, yellow, a little complex. There's a bunch of redsies around North America. And so this is telling us that this land's going in one direction, that's still coming up. What does it mean about this area in red? If this is coming up, this is going down, what's going on off either the west or east coast of North America? That's coming up. Blue up, down. What's going on? They're growing apart, but it's telling us that right now, the coastlines of North America are sinking. Locally, there's variations in that, but they're sinking just because of this isostatic rebound. This is left over from the Ice Age. So part of the reason that there's a lot of problems along the East Coast is it's sinking. How much? That much a year. Doesn't seem like much. Give it 500 or 600 years. It's that much. Okay, so it's a complex mess. It depends, it's gonna get hairy because it depends on how much melting and where you're melting. There was a website that showed up a few years ago that basically said, if you live here, this is what your relative sea level will be predicted to be. But they were making a big deal because for 2 decades we've been fighting about whether most of the sea level change comes from here or Antarctica. And whether one or the other melted would make a difference in the pattern. We're not going to go into that details, but you can go on a website now and somebody has done all this fancy math, and it's really hairy math, to figure out what you're going to do. In fact, I think you're going to get that chance to play with that exercise like assignment 2. This is in the account. The point is, this is taken into account. Oh, we got an assignment already. Before we go any further, should we ask questions? Lady with the red, what questions, what pressing questions, red drinky thing, whatever they call. What are those things called anyway? No, just a water bottle? Oh, it can't be that simple. You don't what? You don't know. Now, do you, so can you do that already? Well, why don't you read it and we'll get back to you, because if we can't read it and do it, then there's questions, and we'd like to ask questions because we sometimes can answer them. The lady beside her, what do you need to know? There, she's working. You already had your turn, didn't you? The lady with the green water bottle. What do you want to know? So basically, this is our data gathering exercise. We're going to think about ice volume and how it converts to equivalence to sea level change. This is an interesting thing we'll tell you all and more than you want to know about sea level change. Buried in it is a conversion factor that you want. So I'm forcing you to skim it to find the conversion factor you want. Okay? It'll tell you exactly if you want to change sea level a millimeter, how much ice you have to change, you have to melt to get that. It doesn't matter if it was the old glacier ice or the modern ice, it's all the same. So this is really set up, what if you melted the modern glaciers, how much sea level you have. So that's how much ice does it take in cubic kilometers, which is a big number. And these are going to be a big number. It's going to be thousands of cubic kilometers to raise sea level a meter. I think you'll find it very handy. If you're not comfortable with it, let's talk about it, but using exponential notation rather than, because you're going to get a bunch of zeros. Lots of zeros, and then people like to drag it out and put a decimal point on the end. Well, most of those digits don't mean anything. So if you just stick with the number part and do your math and the right number of zeros, it will come out a lot easier. So this is review. This is stuff we've talked about. It's focused on Antarctica because it's from a website about Antarctic glaciers. Okay, we're going to estimate how much it takes to raise sea level. So far, no. Did you have a question now?
Yeah, how do we go about estimating?
How do I know what?
How do we go about estimating the
Someplace buried in here is the conversion factor. To get a millimeter, now a millimeter is how much of a meter? How many millimeters in a meter? Well, that's easy to look up. We can find that, okay? And so it's going to tell you how big the answer is going to be in meters cubed. But that's not going to do us any good, right? Because I want it in kilometers cubed, because meters is way too big a number to deal with. So we're going to change, we've got to do some changes with the units, but the math is that one simple formula, that number. I don't know what it is off the top of my head. Lady next to her, the Cincinnati shirt. What have you got?
I think I found.
You found the number?
Yeah.
Oh, sell it at the highest bidder.
I mean, on page 8.
All right, so what kind of number is it? What kind of number is it really? I mean, it's no secret that the number is here. I'd rather you read a little bit to find it, but I'll put it up on the board just so you see what it's roughly. I don't know if you're getting the right one. What do you got?
Okay, so it says a 1 millimeter increase in global sea level requires 10 to the negative third meters cubed.
That's so let's say that again. A millimeter of sea level rise needs how much?
10 to the negative third
Some fancy number,
meters cubed.
meters cubed.
But then it also says in parentheses, or 10 to the negative 12
Oh,
kilometers.
now we're getting too confusing. But there is a formula, there's a number there, right?
Yeah, but then it also gives what it would be in kilometers.
Okay, so with that information, sir, what are you going to do for math to get to an answer, to go from millimeters to meters, right? And meters cubed to kilometers cubed. So you have to do two different adjustments, right? What's the best way to get that kind of information to be sure we're getting it?
For me, I just simply, like, I get a number and I change it to the scientific calculation.
Okay,
Yeah, and like for about for example, 20 is 2 times 10.
correct?
That is
10 to the 1.
10's power.
Right.
Yeah, and I use that.
Okay.
That's a simple way.
So I think there's a number in front of this too. This isn't This isn't a one-to-one number,
That's,
but so back to the thing of about a millimeters. How big is a millimeter? So the first conversion I've got to do to get from here to where I want to be is talk about, there's a meter, there's a millimeter. How many millimeters in a meter? Milli, it's Latin for, abbreviation for.
like 10 times, I mean, it's 1 times 10.
Millimeters, 1,000 millimeters in a meter. 10 millimeters per centimeter, 10 centimeters per, 100 centimeters per meter, right? So there's 1,000 milliliters. So the first thing it's going to do is get 1,000 in here someplace. And then follow this gentleman's suggestion to get the notation right. Anybody have a question so far? That's part one. Let's do part two. Compare that to the amount of water stored in the various parts of the hydrological system. You've seen this graph before. This version has numbers on it. This has got two kinds of numbers on it. Don't confuse the two. This talks about how much is in the ocean. There's 1,335,000 cubic kilometers in the ocean. So if you want to raise sea level a meter, can't get it from the ocean. What I'm asking is where can you get that much water? You're going to get a big number of water, and where can you find it? Permafrost. You hear a lot about permafrost melting. I can tell you that 22 kilometers cubed of melting permafrost won't make a big dent in the ocean's volume. The other thing that's on here are these fluxes. This is how many cubic kilometers per year you would take. So once we find out how many cubic kilometers you take, I could say, well, let's look at how long it would take the rain, 113 kilometers, cubic kilometers every year to get a sea level, meter to rise sea level. It's kind of a nonsensical question because there's this much evaporation going on and it's running through here. So the point is, this is the hydrological cycle. I think we've seen it a little bit before. We're going to get into it more. And there's a couple places that are good candidates to have a meter's worth of sea level in them. Shall we adjourn? You want to stay and thrash with this a bit? I can make sure you get the right number of exponents and all of that stuff. Or not. Otherwise, let's reconvene on Thursday and do our thing.